Hi folks, these are the notes for points, lines, and planes. Make sure you're following along and completing the notes in Kami. So a lot of this is vocabulary based today. We do have 6 slides, which ends up being 3 pages for you to fill in the blanks for the notes and then draw some things. The first word that a lot of you were familiar with already based on the discussion posts is a point. A point has no size or shape, which means that it's undefined, and it gives or denotes a location. A lot of you said it was like a point on the graph, a location on the graph. So that is absolutely right. So we can have a point, a point, a point. We can have lots of points. We can name them. You always want to name a point with one capital letter. So we could name this point A, we could name this point B, we could name this point C. If that bothers you that it's out of order, you need to make sure that you're really conscious about where your points are and what they're named. That'll be important later. So you always want to name with one capital letter. So an example might be point B. And when you're talking, you want to make sure that you say it correctly, so you would call it point B. The next term we're going to define is a line. A line is a set of collinear points that continue in both directions, without end. Without end, in both directions without end. That means it has an undefined thickness, and it goes in both directions without end. So an example of that, we've got 2 ways we could name a line. An example of that would be this one right here. It has multiple points. In fact, it has multiple points between those other points that are named. We just can't really see them because all together they blend together and they make a line. So you want to name a line with 2 points and a line over. So an example might be for this line right here, it's got a point A and a point B on it. So we might say that this is line A, B, and it has a line over it. Make sure that you involve your arrows on both ends. Include your arrows on both ends, because that shows that it does extend forever in both directions. We might also say, and that's referring to this example, we might also say that this is line and then a lowercase, usually cursive letter, so line M. So you would say line AB or you would say line M. A non-example, something that you should not write, and I'll go ahead and switch to red here. A non-example would be using the lowercase letter, but then putting the line on top of it. This is not a good idea. That does not refer to line AB or line M. That is not anything. So make sure that you label your lines correctly. Collinear. So collinear is points that lie on the same line. Same line. So points A and B and C are collinear. In addition to that, points D and C are also collinear. So they're on the same line. Points A and D and B kind of make almost like a triangle here. And we say that those are non-collinear. So either points are collinear or they are non-collinear. As a set of 4 points, so A, B, C, and D, all of these points together as a whole set are not all on one line because we have this point kind of laying outside of this main line. And so we say that as a set of 4 points, these are also non-collinear. Okay, so just a couple interesting things about this diagram right here. So I'm looking at the diagram. Points D and C are collinear. Truthfully, as any 2 points, that you can name. Those points are always going to be collinear, so we're going to find that out in a moment in a postulate. But something that I want to mention is that if I had points A and C and B and my line drawn, and this dotted line wasn't drawn at all, I just had this floating point D out there, there is a line that is kind of invisible between points D and C, or joining points D and C. I could also draw a point down here and name it point F, and there is an invisible line CF that joins point C and points F. So there is an invisible line between point C and point F joining those two. So here, out to the side, I have a little space for you to write that this is a non-visible line. Just because it isn't drawn doesn't mean it doesn't exist. So just because it isn't drawn doesn't mean doesn't mean it doesn't exist. Okay? So just because a line isn't drawn doesn't mean it doesn't exist. So if I've got a floating point, there's a line between C and F, there's a line between B and F, there's a line between A and F. So those are all kind of non-visible lines. Moving on to a plane. A plane, which some of you were already familiar with, is a flat surface with undefined thickness. So think about like a piece of paper. Even though a piece of paper has thickness, you can't really tell how thick it is. To us, it just seems like super thin. But a flat surface with undefined thickness is a plane, and a lot of times paper represents our planes. So a flat surface with undefined thickness. And it continues in all directions without end, just like a line. So I don't have anything drawn for you because I want you to practice drawing a plane. It kind of looks like a parallelogram. Kind of a slanted like rectangle. We'll learn about parallelograms later. You want to name planes with the word plane and one capital letter. So we might call this plane R, and it might have like some kind of, a lot of times it's like cursive, like a script letter, kind of a cursive R there. You can also name a plane with 3 non-collinear points. So I might have, from my previous example, I might have A and C and B be collinear points, and then I might have point D floating out here. And so I might say from before that I knew points A and D and B were non-collinear. So I might call this plane A, D, B. A non-example of a plane would be plane A, B, C. And I'll let you think about that for a second. Why might that be a non-example? Remember that if you're naming planes with 3 points, they need to be non-collinear. And points A, B, and C are all collinear. And so I can't name this plane as plane ABC because A and B and C are all collinear points. Next up is a line segment. A line segment is a part of a line with 2 endpoints. And all the points that are between. So it looks very much like a line because it's part of a line, but we do have these 2 endpoints instead of arrows. So we want to name a line segment with 2 points and a segment over it. So an example might be that I'm going to call this segment AB. I could also switch around and call this segment BA, as long as the endpoints are A and point B. Okay. The way I say this is line segment AB, so you want to make sure that you're saying it correctly so that you sound like you know what you're talking about. And then a non-example, whenever you name line segment AB, would be taking the A and the B and putting a segment on top, but then putting kind of points at the end. That's something that you don't want to do. Okay, so that's a no. And then you also don't want to just leave it as AB, because that refers to something else, and we're going to find out what that is in a few days. Those are not things that you want to do. You want to stick with the 2 letters that are the endpoints and then just kind of a bar on top. Let's move to array. Some of you knew what array was. It's part of a line with 1 endpoint and all the points to one side. So when you think about array, you might think about a sun ray or some other kinds of rays. You might think of a sun ray, though. That's the one that most people point out whenever we first start talking about rays. And a sun ray radiates from the sun, so it radiates from one endpoint and then goes out and covers all the points to one side. So that's a ray. I'm going to draw one that's a little bit bigger. So here's my end point and all the points to one side. Because there are all of these points on one side, I might have some other points that are labeled. So maybe this is point C, point B, point A. I'm intentionally doing these not in alphabetical order so that you get used to seeing points that are not in alphabetical order. So each of these points make a ray. But if you're going to refer to the whole thing, the big one, you need to start with the endpoint C. So like if I start here and I just consider this, that's ray A. If I start here and I consider this, that's ray B. But if I want to refer to the whole thing, then I want to call that something that starts with the endpoint C. So when you name a ray, you're going to name a ray with 2 points and a ray over it. You always want to start with the endpoint when you're naming. And you always point your ray to the right whenever you're actually writing the name of the ray. So if I'm referring to this big ray, the entire thing, the end point is point C. So the example would be that I might call this ray CB, because I want to use 2 points, but I want to start with the end point. So I've used 2 points on the ray, but the end point is point C. I could also call this ray CA, because I use 2 points on the ray, but I start with the end point C. Some non-examples would be ray BC. So the issue with this is that we're using 2 points, but we didn't start with the end point. So that's not a good example. AC, ray AC, for the same reason, does not refer to the entire large ray because we're not starting with the end point. And finally, ray CB is good, but remember the arrow points to the right. If you have an arrow pointing to the left, that is not referring a ray. That is incorrect. Sorry, referring to a ray. That is incorrect. Okay. So we've got one more term, and then we're going to start talking about some postulates. The last term is opposite rays. It's kind of a confusing term whenever you start seeing it in your assignments. So make sure you refer back to these notes and the definition when you start seeing opposite rays. So opposite rays is a pair of rays with a common endpoint. A common endpoint, and together they form a line. So I'm going to change my color here. And I'm going to give you an example and a non-example. So an example of opposite rays would be ray CB. Remember ray CB? Remember ray CB denotes the ray that starts at endpoint C and it goes through point B. So it's talking about that part. Okay? So this is ray CB. And if I'm talking about its opposite ray, CB and ray CD are opposite rays because CD refers to this ray right here. Okay. So both of these are point C. We have ray CB and ray CD. Notice how they have a common endpoint, that's endpoint C, but together they form a line. So this is a good example. A non-example would be ray CB and ray BC. Let's look at why. So I'm going to draw this underneath. Ray CB, just like before, starts at endpoint C and it goes through point B. Okay, so that's looking pretty good. But the second ray that I said was ray BC, which means that that starts at endpoint B and it goes through point C. So I noticed that we don't have a common endpoint here. In fact, just by looking at the first letters of the name, those are not the same. So this is a non-example. And the reason it's a non-example is because opposite rays cannot overlap. This overlapping area that we have right here, that cannot happen. Okay? So those are not opposite rays. So now we're going to move into postulates. Postulates are kind of just statements that are accepted to be true. They are kind of the foundations of some of our geometric concepts. And so postulates are something we want to start out the year with because we want to understand more of the basics of geometry and why things are the way that they are. So I always start out with the first part and then I let you fill in the second part. So the first postulate is if 2 points are in a plane, then the line containing them is 2. So there are a couple ways that we're going to talk about intersecting figures. So I'm going to jump from the picture all the way over here. It says 3 ways a line and a plane intersect. And when you think of intersect, you probably think from Algebra 1 and Algebra 2, you think of like crossing or where like something passes through something else. An intersection, let me change this. There. An intersection isn't a passing through. It's what 2 figures have in common. It's what they share, what they have in common. So we're going to talk about the 3 ways that a line and a plane can intersect, meaning the 3 situations where they might have something in common. So the first situation is what you see with the plane and the red line. The line passes through the plane. So think about a pencil sticking into a piece of paper through a hole and then going out the bottom of the paper. So the line is passing through the plane. That means the intersection is that hole that the pencil made with the paper, and that represents a point. So this right here is the intersection. It's what they have in common. This point lies on the red line, but this point lies also in the plane. So this point is what they have in common, meaning that point is the intersection. I'm going to skip down to the bottom one. The bottom one refers to the blue lines, where a line is parallel to a plane, meaning they don't touch. Remember, things that are parallel mean they go in the same direction forever and ever, and they don't touch. So if we have blue lines that are parallel to our plane, that means they're never going to touch. So can they have anything in common? The answer is no. they have no common points, so there's no intersection. And then finally, we're going to talk about this green line. The green line lies on the plane. So think about a piece of paper as your plane, and think about a pencil sitting on that piece of paper. Think about what those two figures have in common. Those two figures have all points in common that are on the line, right? Because the pencil is touching the paper at all places. So the intersection is actually the whole line. The entire line is the intersection, because this point and this point and this point and this point and all the points that are on that line, not only are they on the line, but they're also lying on the plane, since the line is on the plane. So that means all those points are shared by the plane and the line. So the whole line is the intersection. Next postulate. The next postulate says if two lines intersect, then they intersect at exactly 1 point. So an example of this, if you were trying to model it at your house, might be 2 pens or 2 pencils, and you're trying to see how many times they touch, how many times they cross. You can't cross them more than once unless you break one of them. Some of you may be thinking, well, if I have, let's use green. If I have one line and I have a line going through right here, well, then I can just bend it over and I can make it intersect at 2 different points. That brings us to our next piece of information, is that all lines are straight. All lines are straight. So if a line, in parentheses, if a line curves, then it is not a line. It is a curve. So this example that I drew here, this first green piece, that is a line, but this second green piece is not a line, that's a curve. In fact, it almost looks parabolic. So that is a curve. And they intersect at 1 point. We might call this point point P. You can call it whatever you want. Next postulate. If 2 planes intersect, then they intersect at exactly 1 line. So what I want you to think about here is I want you to think about 2 pieces of paper that might be somehow crossing each other. Maybe you've cut slits in the middle and you've kind of made them connect. And then this is a line that is not only lying in plane B, but it's also lying in plane Q. And it's difficult to visualize, so if you need help, ask me to Zoom with you and I'll show you kind of a 3-dimensional representation. So if I have both plane Q and plane B, and I have line XY that's lying in both of them, that means that plane Q and plane B intersect at that line. So 2 planes intersect at exactly 1 line, and here they're intersecting at line XY. Remember, you write a line with 2 capital letters referencing the points and a line on top. That brings us to the next point, which is any 3 collinear points. So maybe points X and Y and maybe point Z in here. They're collinear because they all fall on the same line. Any 3 collinear points have an infinite number of planes through them. The reason for this is that you can take either of these planes and you can kind of spin it and rotate it around that line XY. So again, if you're having trouble visualizing this, ask to Zoom with me, maybe in tutorials, and I'll help you to visualize it. But any 3 collinear points have an infinite number of planes through them. We're almost finished, folks. Hang on in there. The next postulate is through any 2 points, there is exactly 1 line. So I've given you 2 points here, And if you can put a line through it, you'll notice that it's the only line that you can draw. Remember that any quote-unquote line that curves is not a line, it's a curve. So the only thing that goes through points X and Y that is a line is this right here, and it is unique. It is the only one that goes through points X and Y. Through any 2 points there is exactly one line, meaning you can't draw more than one. This is it, exactly one. So any 2 points, and we referenced this at the beginning, any 2 points have exactly one line going through them, so any 2 points are collinear, meaning they have a line going through them. So this is kind of a postulate that seems like, why in the world do we talk about this? But it needs to be mentioned. Through any 2 points, there's exactly one line. And then finally, through any 3 non-collinear points, there is exactly one plane. So here I have a prism for you. If you want to imagine like a box that you get from a store or Amazon or something like that, it might help you visualize. So we want to say that through any 3 non-collinear points, there's exactly one plane. So if I take any 3 non-collinear points, so maybe point A, point D, and then something that's not on line segment AD, so A and D and C. The plane that goes through those 3 points is actually this plane right here, up at the top. So that plane goes through point A and D and C. So we might call that plane ADC. Notice that it's the only plane that goes through those 3 points. The front of the box doesn't go through those 3 points because it doesn't go through point A. So that plane is unique. Some people in class ask, well, Ms. Belsick, what about planes that are not making up a side of the box? So they ask about like maybe point A and point D and point H or something like that. And the answer is that yes, those are 3 non-collinear points, and there's still exactly one plane that goes through them. And that one plane is made up like this. So imagine that there's some kind of like diagonal piece of cardboard that you're inserting into that box, and it doesn't quite fit, so it kind of leans down here at the bottom, and then it also leans out here at the top. So there's still that one plane that's kind of slicing into that prism. So any 3 points are always going to make exactly one plane, so we say any 3 points are co-planar.